Have you ever looked up at the night sky and felt that tug of wonder, the kind that makes you question everything you thought you knew about the universe? Maybe you've heard the wild stories about black holes swallowing entire galaxies, or whispers of alien civilizations lurking in distant star systems. Some of these tales sound like science fiction, but what if the truth is even more extraordinary? Today, we're peeling back the layers of cosmic mystery to reveal what's really happening out there in the infinite expanse. This isn't just about stargazing, it's about confronting the myths that have shaped our understanding of the cosmos and discovering the jaw-dropping science that proves reality is often stranger than fiction. Think about the stories passed down through generations, legends of rogue planets on collision courses, or nebulae that birth new stars like celestial fireworks. Some of these ideas have been etched into our collective imagination, but how many of them hold up under the cold, hard light of scientific scrutiny? The universe doesn't owe us easy answers, and that's what makes unraveling its secrets so thrilling. From the mind-bending physics of wormholes to the eerie silence in our search for extraterrestrial life, every discovery leads to more questions. And that's where the real adventure begins. So let's set the record straight. This journey isn't just about debunking myths. It's about celebrating the astonishing truths that lie hidden in the cosmos. We'll explore how black holes really behave, why distant galaxies defy our expectations, and whether we're truly alone in this vast universe. Along the way, you'll encounter revelations that challenge everything you thought you knew, because the universe has a way of humbling even the brightest minds. By the time we're done, you'll see the night sky not just as a blanket of stars, but as a living, breathing mystery waiting to be solved, ready to dive in. The cosmos has been keeping secrets, and it's time we uncovered them together. Humanity has always gazed at the stars and seen more than just points of light. We've seen stories. Ancient cultures watched comets streak across the sky and imagined them as omens of war or famine. The Greeks saw constellations as gods and heroes frozen in the heavens, while sailors navigated by myths as much as by the North Star. Even today, when science has given us telescopes and satellites, we still cling to cosmic tales that defy logic. Why? Because the universe is vast, mysterious, and often terrifying in its silence. Myths fill the gaps where knowledge falters, turning the unknown into something familiar, even comforting. Take something as simple as a solar eclipse. For millennia, civilizations from China to the Maya interpreted it as a dragon devouring the sun or a celestial battle between light and darkness. These weren't just guesses, they were attempts to make sense of a world that seemed chaotic. Our brains are wired to seek patterns, to connect dots even when no lines exist. It's called apophenia, the tendency to find meaning in randomness. When faced with the incomprehensible scale of the cosmos, it's no wonder we invent narratives to tame the chaos. But it's not just ancient history. Modern myths thrive because they tap into the same primal instincts. Think about the persistent belief in a so-called moon landing hoax, or viral claims that a rogue planet will collide with Earth. These ideas spread not because they're true, but because they're dramatic. They transform cold, impersonal astronomy into a gripping saga of deception or doom. Hollywood amplifies this, turning black holes into time portals and aliens into either saviors or invaders. The more we see these stories on screen, the more they seep into our collective imagination, blurring the line between fact and fiction. So how do we separate cosmic truth from captivating lies? It starts with curiosity, not just about the universe, but about our own minds. Recognizing that we're prone to storytelling doesn't make us gullible, it makes us human. The real magic happens when we channel that same wonder into questioning, testing, and embracing the messy, awe-inspiring truth science reveals. After all, the cosmos doesn't need myths to be extraordinary. A supernova's death throes or the dance of colliding galaxies are more breathtaking than any legend. The universe's greatest secret might just be that reality, once understood, is more dazzling than anything we could invent. One of the most stubborn myths about our cosmic neighbor is the idea that the moon has a permanent, dark side, a mysterious hemisphere forever shrouded in eternal night. We've heard it in songs, seen it in movies, and even used the phrase casually in conversation. But here's the twist: science tells us that claim couldn't be further from the truth. The so-called dark side isn't actually darker than the side we see from Earth. It's just hidden from our view. This misconception starts with a simple quirk of celestial mechanics called tidal locking. Over billions of years, Earth's gravity has slowed the moon's rotation until it matches its orbit around our planet. That means the same face always points toward us, like a dancer spinning perfectly in sync with their partner. But while we only see one side from Earth, sunlight doesn't play favorites. The far side, often mislabeled as the dark side, cycles through day and night just like the near side, basking in sunlight for about 2 weeks at a time before dipping into an equally long lunar night. So where did the myth come from? Blame pop culture. Pink Floyd's legendary album, The Dark Side of the Moon, cemented the phrase in our collective imagination, even though astronomers cringe at the inaccuracy. Science fiction didn't help either, often depicting the far side as a shadowy realm of alien bases or lurking dangers. But reality is far more fascinating. When China's Chang'e 4 probe landed there in 2019, it sent back images of a sunlit landscape, rocky, cratered, and utterly bathed in light. The truth is, the far side isn't dark. It's just different. Without Earth's reflected light, its nights are pitch black, and its radio silence makes it perfect for telescopes. But the real magic lies in what this teaches us about perception. The moon doesn't have a dark side. It has a hidden side, one we couldn't see until technology pulled back the curtain. And that's the beauty of space exploration. Every myth we debunk reveals a truth more intriguing than fiction. Black holes have long been cast as the ultimate villains of the cosmos, ravenous monsters lurking in space, sucking in everything that dares to wander too close. It's an image burned into our minds by movies and TV shows, where these gravitational behemoths devour stars, planets, and even light itself with indiscriminate hunger. But here's the cosmic reality check. Black holes aren't the all-consuming vacuum cleaners we've been led to believe. In truth, their behavior is far more nuanced, governed by laws of physics that are stranger and more fascinating than any Hollywood script. Let's start with the basics. A black hole's power comes from its unimaginable density, packing the mass of multiple suns into a space smaller than a city. This creates gravity so intense that not even light can escape once it crosses a point of no return called the event horizon. But here's the catch: that gravity behaves just like any other force in space. Planets don't get sucked into the sun, they orbit it. Similarly, stars and gas clouds can dance around a black hole for billions of years without ever falling in, as long as they maintain a safe distance. The Milky Way's supermassive black hole, Sagittarius A star, is proof. It's surrounded by a bustling stellar neighborhood, with stars whipping around it at blistering speeds, held in place by the same delicate balance that keeps Earth circling our sun. Now, if an object does venture too close, that's when the real cosmic drama unfolds. The intense gravity doesn't just pull, it distorts. Imagine falling feet first toward a black hole. The gravitational force on your feet would be exponentially stronger than on your head. stretching you into a thin, noodle-like strand in a process scientists call, with perfect seriousness, spaghettification. Time itself warps near the event horizon, slowing to a crawl from an outside observer's perspective while racing forward for you. These aren't sci-fi exaggerations, they're the proven predictions of Einstein's theory of relativity. So why does the vacuum cleaner myth persist? Part of it comes from how we visualize black holes. Artists' renditions often show them as whirlpools in space, dragging matter inward like water down a drain. But real black holes are messier. They're surrounded by swirling disks of superheated gas and dust, where friction and magnetic fields sometimes fling material away at nearly the speed of light in dazzling jets. These outbursts can outshine entire galaxies, proving that black holes aren't just takers, they're creators too, shaping the cosmos around them in ways we're still unraveling. The next time you hear someone describe black holes as cosmic vacuum cleaners, remember, the truth is infinitely more interesting. These enigmatic objects don't just destroy, they sculpt, they illuminate, and they challenge everything we know about the fabric of reality. And that's a story worth telling. Here's a myth you've probably heard 100 times: the Great Wall of China, that ancient serpent of stone winding across mountains and deserts, is so massive it's the only human-made structure visible from space. It sounds impressive, like a testament to human ingenuity stretching so far it can be seen from the cosmos. But here's the twist: it's completely untrue. Astronauts orbiting Earth have confirmed time and again without magnification. The Great Wall is nearly impossible to spot with the naked eye. From space, it blends into the natural contours of the landscape, just another thread in the tapestry of Earth's terrain. So how did this myth take hold? The story likely grew out of early spaceflight enthusiasm, when the idea of seeing human achievements from orbit captured the public's imagination. Exaggeration spread, turning a poetic notion into accepted fact. But the reality is far more humbling. Earth's atmosphere, curvature, and the wall's own narrow width, averaging just 6 meters across, make it vanish against the backdrop of forests, deserts, and mountain shadows. Even from the International Space Station, which orbits at around 400 kilometers up, spotting the wall is like trying to pick out a single gray shoelace draped across a football field. Now, satellites with high-resolution cameras can indeed detect the Great Wall, but here's the catch: they can also spot highways, airports, and even large ships at sea. That doesn't mean those structures are visible to human eyes unaided. The myth crumbles further when you realize other colossal human creations, like cities or sprawling agricultural fields, are far more obvious from orbit. The Great Wall's fame simply outpaced its visibility. What makes this myth so enduring? It taps into something deeper than trivia. It's about our desire to leave a mark so grand it transcends Earth itself. The truth, though, is even more profound. From space, what astronauts actually see are the fragile boundaries of our planet, the thin blue line of the atmosphere, the interconnected web of rivers and coastlines, and the glowing grids of human civilization at night. The Great Wall's invisibility from orbit isn't a failure. It's a reminder that nature's scale dwarfs even our mightiest efforts, and somehow that's even more awe-inspiring. Astrology has captivated humanity for thousands of years. Generations of kings consulted star charts before waging wars. Modern apps deliver daily horoscopes with a tap, and millions still check their zodiac sign before making big decisions. It's woven into our culture, language, and even dating apps. But here's the cosmic truth: no peer-reviewed study has ever found evidence that the position of stars and planets at your birth shapes your personality or destiny. So why does it feel so real? The answer lies not in the heavens, but in the quirks of human psychology. Take the Barnum effect, a phenomenon where people believe vague, general statements are uniquely tailored to them. Psychologist Bertram Forer proved this in 1948 by giving students a personality test, then handing them identical horoscope-style readings filled with broad platitudes like, "You have a great need for others to like and admire you." Nearly all rated the descriptions as uncannily accurate, even though everyone received the same text. That's the magic trick behind horoscopes. They're crafted to be just ambiguous enough you're facing challenges but have hidden strengths that anyone can project their own life onto them. But what about the stars themselves? Astronomers point out a glaring flaw. The zodiac signs we use today are based on constellations as they appeared over 2,000 years ago. Due to Earth's axial wobble called precession, those constellations have shifted by nearly a full month. So if you were born under Leo, the Sun was actually in Cancer at the time. Even if astrology worked, we've been using the wrong star maps for centuries. Then there's the statistical evidence. Researchers have conducted double-blind studies where astrologers tried matching birth charts to real people and performed no better than random chance. In one famous experiment, astrologers couldn't even distinguish violent criminals from peaceful volunteers based on their star signs. The universe doesn't care when you are born. Gravity and light operate the same way for everyone, regardless of zodiac signs. So why does astrology persist? Because it offers comfort. In a chaotic world, the idea that celestial bodies guide our lives gives an illusion of order. But here's the beautiful paradox. Science reveals a cosmos far more wondrous than any horoscope. The real magic isn't in fictional planetary influences, it's in our ability to question, explore, and find meaning not in the stars but in ourselves. Perhaps no space myth has sparked more debate than the stubborn claim that the Apollo moon landing in 1969 was an elaborate hoax. Conspiracy theories range from staged studio footage to accusations that the entire space race was fabricated to win Cold War bragging rights. But here's what often gets lost in the noise. Science doesn't deal in speculation. It deals in evidence, and the proof that humans walked on the moon isn't just overwhelming, it's still being used by researchers today. Take the lunar laser ranging experiments. When Apollo astronauts left retroreflector arrays on the moon's surface, they weren't just planting flags, they were setting up mirrors. For decades, scientists have been firing lasers at these reflectors from Earth, timing how long it takes for the light to bounce back. The precision of these measurements, accurate down to a few centimeters, has helped us study everything from the moon's gradual drift away from Earth to the nature of gravity itself. If the landings were faked, how could these reflectors, still functioning after 50 years, be returning data that aligns perfectly with independent astronomical observations? Then there are the moon rocks. Hundreds of kilograms were brought back by Apollo crews, each sample bearing unique chemical signatures impossible to replicate on Earth. They lack water molecules, show evidence of being bombarded by solar wind, and contain isotopes only formed in the vacuum of space. Geologists worldwide have studied these rocks, and not one has ever found a discrepancy pointing to an earthly origin. Even the Soviet Union, America's space race rival, analyzed Apollo samples and confirmed their authenticity. Why would competing superpowers collaborate to uphold a lie? But what about the proof of fakery? Conspiracy arguments often hinge on perceived anomalies, flags appearing to wave in a vacuum, odd shadows, or the absence of stars in photos. Each has a simple scientific explanation. The flag's movement came from astronauts twisting it into the lunar soil, creating ripples in the fabric. Shadows appear uneven because the moon's surface is uneven, with slopes and craters scattering light. And stars aren't visible in photos for the same reason they're invisible in daylight on Earth. The bright lunar surface overexposes the camera, washing out faint starlight. These aren't signs of a cover-up, they're the predictable results of physics. So why does this myth endure? At its core, it's less about the moon and more about human nature. The late 1960s were a time of deep societal distrust. Vietnam, Watergate, and political assassinations eroded faith in institutions. A moon landing, broadcast live but witnessed firsthand by only a handful of astronauts, became a canvas for suspicion. But here's the irony. The very technology conspiracy theorists used to spread their claims, global communication networks, high-resolution imaging, exists because of the space program they dismiss. The truth is, debunking moon landing myths isn't just about correcting facts. It's about celebrating one of humanity's greatest achievements without the shadow of baseless doubt. When you look up at the moon tonight, remember there are footprints up there, preserved in vacuum for millennia, waiting for the next explorers to add their own. And that's a story no conspiracy can erase. That shimmering streak you just wished upon, it wasn't a star at all. The truth behind shooting stars is one of the cosmos' most beautiful deceptions, a fleeting light show born from cosmic crumbs rather than distant suns. Those bright dashes across the night sky are actually meteors, often no larger than a grain of sand, vaporizing in a blaze of glory as they slam into Earth's atmosphere at speeds exceeding 200,000 kilometers per hour. The friction of their descent heats them to thousands of degrees, ionizing the air around them and creating those brilliant trails we admire. Stars, by contrast, are colossal nuclear furnaces light years away, so distant that their light takes years, centuries, or even millennia to reach us. The myth's endurance is poetic. Ancient cultures saw these sudden flashes as stars dislodged from the heavens, divine omens or celestial messengers. Even today, the phrase "shooting star" persists in songs, stories, and birthday wishes. But science paints a far more dynamic picture. Most meteors originate from debris left behind by comets, those icy travelers that shed dust and rock as they orbit the sun. When Earth's path crosses these cosmic breadcrumbs, we get meteor showers like the Perseids or Geminids events where dozens of shooting stars streak across the sky each hour. Here's where it gets even more fascinating. What we call a meteor is only the visible part of the story. Before it hits our atmosphere, the particle is a meteoroid, a fragment drifting in space. If it survives its fiery plunge and lands on Earth, it graduates to meteorite status, and size doesn't always dictate spectacle. A pea-sized meteor can outshine Venus because its energy comes from velocity, not mass. So why does this distinction matter? Because every streak of light is a reminder of our solar system's messy, chaotic beauty. Those falling stars are proof that space isn't some static painting. It's an ever-changing arena where tiny rocks can put on a show rivaling the grandest celestial objects. The next time you spot one, remember, you're not watching a star's death throes. You're seeing a speck of cosmic dust, perhaps older than Earth itself, writing its final chapter in a blaze of light, a humble reminder that even the smallest things in the universe can leave us breathless. Silence in space isn't what we think. The common image of a vast, soundless void comes from a basic truth: sound waves need a medium like air or water to travel, and the vacuum between stars offers none. But to say space is utterly silent misses something extraordinary. The cosmos hums with electromagnetic energy, and with the right tools, we can translate those invisible vibrations into sounds that defy imagination. Imagine Saturn's rings not as frozen bands of ice, but as a celestial choir, their particles colliding in rhythms that, when sped up, create an eerie, metallic symphony. Or Jupiter's magnetosphere, a swirling storm of charged particles, converted into a deep, pulsing roar that sounds more like a science fiction soundscape than anything from nature. NASA spacecraft have become our cosmic ears. The Cassini probe, for instance, recorded radio emissions from Saturn's Auroras crackling, ghostly whispers that reveal the planet's magnetic dance with the solar wind. Juno, orbiting Jupiter, captured the chaotic chorus of its magnetic field, a cacophony of pops and whistles created by electrons spiraling along invisible force lines. These aren't just scientific curiosities, they're proof that the universe communicates in frequencies beyond human hearing, waiting for us to decode them. So why does the myth of absolute silence persist? It stems from how we experience sound on Earth. We're used to vibrations traveling through air, so the idea of a place where screams or explosions would go unheard feels unsettling. But space doesn't play by our rules. Instead of sound waves, it uses plasma waves, magnetic oscillations, and charged particle interactions, all of which can be translated into something audible with the right technology. The Voyager probes even picked up the interstellar medium's faint hiss, the background noise of the galaxy itself. This revelation changes how we perceive the cosmos. Space isn't a silent movie, it's more like a radio broadcast we've only just learned to tune into. Each planet, each star, even the emptiness between them has a signature sound, a hidden layer of reality that's as awe-inspiring as any visual spectacle. The next time you gaze at the night sky, remember, the universe isn't mute, we just needed to learn how to listen. We think we know the dimensions of our universe, 3 for space, 1 for time. That's the world we see and move through every day. But what if our reality is just the surface of something far deeper? String theory, one of the most ambitious frameworks in modern physics, suggests the cosmos might be humming with hidden dimensions, up to 11 of them, curled up so tightly that even atoms seem gigantic by comparison. The idea that we're limited to just 4 dimensions isn't just outdated. It's a cosmic oversimplification that ignores the mind-bending possibilities lurking in the math. So where did this myth come from? It's rooted in how we experience reality. Our brains evolved to navigate a 3-dimensional world: height, width, depth, with time as the invisible 4th dimension. Anything beyond that feels like science fiction. But physics doesn't care about what feels intuitive. When researchers grapple with the universe's biggest puzzles, like why gravity is exponentially weaker than other fundamental forces, or how quantum particles behave in ways that defy classical physics, extra dimensions emerge as an elegant solution. Imagine gravity as a force that leaks into higher dimensions, diluting its strength in our observable world. Or picture tiny strings vibrating in unseen dimensions, their frequencies determining the properties of every particle in existence. These aren't wild guesses, they're predictions flowing from equations that have survived decades of scrutiny. The real magic lies in how these hidden dimensions might be shaped. Some theories propose they're coiled into intricate geometric forms at scales 1 billion times smaller than an atom, like a garden hose that looks one-dimensional from afar but reveals its circular surface up close. Others suggest they could be expansive but invisible, like parallel universes separated by folds in space-time. The catch, we can't yet observe them directly. But absence of evidence isn't evidence of absence centuries ago. No one could see atoms either. Why does this matter? Because it reshapes how we see reality. The universe isn't just stranger than we imagine. It might be stranger than we can imagine. Every time we've peeled back a layer of the cosmos, from realizing Earth orbits the Sun to discovering space-time bends, we've had to abandon comfortable assumptions. Higher dimensions are the next frontier, a reminder that the true nature of existence could be hiding in plain sight. just beyond the limits of our perception. And that's the real beauty of physics. It keeps revealing how much we still have left to discover. Go ahead and grab a box of crayons. Chances are the one labeled Sun is a bright, buttery yellow. From kindergarten drawings to weather app icons, we've been conditioned to think of our nearest star as golden, even though every astronaut who's glimpsed it from space describes it differently, a blinding, pure white. This isn't just a trick of perspective, it's a cosmic magic act performed by Earth's atmosphere. Here's what's really happening. Sunlight contains every color in the visible spectrum, which combined should appear white to our eyes, just like when you mix all the colors on a spinning top. But as that light travels through Earth's atmosphere, shorter blue wavelengths scatter in all directions, which is why our sky looks blue, leaving the longer red and yellow wavelengths to dominate the sun's apparent color near the horizon. At midday, when sunlight takes a shorter path through the atmosphere, the sun looks closer to its true white hue, though most of us still perceive a faint yellow tint. Step outside Earth's air entirely, though, and the illusion vanishes. Photos taken from the International Space Station show the sun as a stark, luminous white disk, its light unaltered by atmospheric filtering. But wait, there's a twist that even surprises many astronomy enthusiasts. While the sun emits light across all colors, its peak wavelength is actually green. Our eyes don't register this because the star's output is so broad spectrum that we perceive the blend as white. It's like listening to an orchestra where every instrument plays at once. You hear the combined richness, not the solo flute cutting through. So why does the yellow myth persist? Blame art and culture. From Van Gogh's swirling suns to the ubiquitous yellow smiley face, we've aestheticized a celestial body that's far more complex. Even language betrays us. Phrases like golden sunshine reinforce the idea. But the next time you squint at the noonday sun, remember, you're seeing a cosmic chameleon, its color shaped not by the star itself, but by the air that keeps us alive. And that's a paradox worth savoring. The same atmosphere that paints our skies blue and sunsets red also obscures the universe's true palette. Perhaps the real lesson here is about perception. The sun isn't changing, our vantage point is, and that's a humbling reminder of how much our everyday experience filters the cosmos. The universe doesn't bend to our expectations. It's up to us to peel back the layers and see it as it really is. When astronomers first spotted the bizarre flickering of Tabby's star in 2015, it ignited a firestorm of speculation. Here was a star officially named KSE 8462852, behaving like nothing scientists had ever seen. Its light dimmed erratically, sometimes by as much as 22%, in patterns that defied conventional explanations. The internet, ever eager for cosmic drama, pounced. Could this be evidence of an alien megastructure, a vast Dyson sphere built by an advanced civilization to harness the star's energy? The idea wasn't just science fiction. It was proposed seriously by researchers as one possible interpretation. For a moment, it felt like we might be on the verge of the greatest discovery in human history. But science, unlike speculation, demands rigor. As telescopes turned toward Tabby's star, a different story emerged. Detailed observations revealed that the dimming wasn't caused by some monolithic artificial construct. Instead, it was vast clouds of dust, uneven, swirling, and oddly clumpy, passing between the star and Earth. These weren't the symmetrical shadows of a megastructure, but the messy fingerprints of natural cosmic debris. Some scientists even suggested the dust might be remnants of a shattered planet or comet, creating a chaotic veil around the star. The truth was far less sensational than aliens, but no less fascinating. What makes this myth so compelling isn't just the allure of extraterrestrial intelligence, it's the way it reveals how science actually works. The initial hype wasn't a failure of the scientific process, it was part of it. Researchers floated the Dyson sphere hypothesis because at the time, it was a plausible explanation that fit the data. But as more evidence rolled in, they pivoted, adapting their understanding to match reality. This is how discovery unfolds, not in dramatic eureka moments, but through painstaking observation, skepticism, and the courage to abandon exciting ideas when they don't hold up. And yet the myth lingers. Why? Because it taps into something primal, the hope that we're not alone, and that the universe might be filled with civilizations grand enough to reshape stars. But here's the irony. Tabby star's true mystery is arguably more intriguing than any sci-fi scenario. Why does it have such irregular dust clouds? What catastrophic event could have created them? These questions drive astronomers to keep studying it, not as a cosmic celebrity, but as a puzzle that could teach us about how planetary systems evolve or fall apart. The lesson here isn't that we shouldn't dream big. It's that the universe rewards curiosity, even when it leads us down unexpected paths. Alien megastructures may remain in the realm of fiction for now, but the real story of a star shrouded in enigma proves that reality, when examined closely, is always stranger than our wildest imagining. And that's a discovery worth celebrating. We've all seen the dramatic illustrations, a single point of light erupting into a fireball, scattering galaxies like cosmic shrapnel. It's how pop culture has depicted the Big Bang for decades, a violent explosion in the void of space, as if the universe were born from some celestial detonation. But here's the cosmic reality check. The Big Bang wasn't an explosion at all. It was something far stranger, the rapid expansion of space itself, unfolding everywhere at once with no center and no edges. This misunderstanding isn't just a minor mix-up. It fundamentally warps how we picture the birth of everything. Think about the difference this way. An explosion, like a supernova or a firework, happens at a specific location, hurling matter outward into pre-existing space. The Big Bang didn't occur in space, it created space. Imagine the universe as a balloon covered in dots. As you inflate it, every dot moves away from every other dot, not because they're being propelled from a central point, but because the fabric between them is stretching. That's the essence of the Big Bang, not a fiery burst, but a smooth, relentless expansion where every point in the cosmos was once unimaginably close together. So where did the explosion myth come from? Blame the name itself. Big Bang was coined sarcastically by astronomer Fred Hoyle in 1949 during a radio debate, and the catchy phrase stuck despite its inaccuracy. Artistic renditions didn't help, favoring spectacle over subtlety. Even today, documentaries and textbooks often default to fiery visuals because they're more dramatic than the abstract truth, a universe stretching like taffy with no flashy flames or shockwaves. But the implications run deeper. If the Big Bang wasn't an explosion, there's no center to the universe, no smoldering crater where it all began. The cosmic microwave background, the afterglow of that early expansion, shows near-perfect uniformity in all directions, like fading heat from an oven that warmed everything equally. This radiation map, captured by satellites like Planck, is our strongest evidence that the universe's beginnings were a synchronized transformation, not a chaotic blast. Here's the mind-bending part. The Big Bang wasn't something that happened somewhere. It happened everywhere, including right where you're sitting. 13.8 billion years ago, this spot, along with every other point in the cosmos, was compressed into an unfathomably hot, dense state. The space between atoms, stars, and galaxies didn't exist yet. There was no outside to explode into. The universe wasn't expanding into anything. It was creating the very concept of into as it grew. Why does this distinction matter? Because it reshapes our cosmic identity. We're not debris flung from some primordial blast site. We're part of a stretching fabric, still riding that initial expansion. Galaxies aren't flying apart, the space between them is growing, and that's the real magic of the Big Bang. It's not a moment we can point to in the sky. It's the story of everything, written in the stretching of space-time itself, a reminder that sometimes the truth is stranger and more beautiful than any myth. For decades, whispers of a rogue planet named Nibiru, or Planet X, have haunted the fringes of astronomy, fueled by claims that this unseen world is hurtling toward Earth with apocalyptic consequences. The story goes something like this. Ancient civilizations predicted its return. NASA is covering up its approach, and its gravitational pull will trigger earthquakes, volcanic eruptions, and tidal waves before a cataclysmic collision. It's a gripping narrative, the kind that spawns blockbuster disaster movies and breathless YouTube conspiracy videos. But here's the problem: not a single shred of credible scientific evidence supports it. Let's start with the basics. If a planet large enough to wreak havoc on Earth were barreling through our solar system, we'd know. Astronomers can detect the gravitational tugs of objects far smaller than a planet. Neptune was found in 1846 because of its subtle influence on Uranus's orbit. Modern telescopes like Pan-STARRS and the Vera-C, Rubin Observatory scan the skies nightly, mapping asteroids and distant objects with pinpoint accuracy. Something as massive as Nibiru, supposedly just years away from impact, would leave undeniable gravitational fingerprints on the orbits of known planets and be visible even to amateur astronomers. Yet after decades of searching, no such planet has materialized. The myth's origins are murkier than its supposed science. The name Nibiru first appeared in the works of fringe author Zecharia Sitchin, who claimed it was a planet described in ancient Sumerian texts. But mainstream scholars and archaeologists universally reject his translations as fictional. NASA has debunked the Nibiru theory repeatedly, pointing out that infrared surveys like WISE Wide Field Infrared Survey Explorer have mapped the solar system's outer reaches without finding any hint of a hidden world. Even the hypothetical Planet 9, a legitimate area of research, is theorized to orbit hundreds of times farther away than Pluto, with no chance of ever nearing Earth. So why does this myth persist? It taps into a deep, primal fear, the idea that doom could come from the sky without warning. From Nostradamus to Mayan calendar hysteria, humanity has a long tradition of projecting anxieties onto cosmic events. Nibiru's staying power lies in its flexibility. Every time a predicted doomsday passes uneventfully, believers simply push the date forward, weaving new justifications into the narrative. Social media amplifies this, turning vague speculation into viral evidence, like mislabeled photos of lens flares or atmospheric phenomena. But here's the real irony. While Nibiru is fiction, the search for unknown worlds is very much real. Astronomers are hunting for distant planets in our solar system's outskirts, not to fuel doomsday prophecies, but to understand how planetary systems form. The difference: real science welcomes scrutiny, adjusts to evidence, and admits when it's wrong. The universe is mysterious enough without inventing threats. So the next time you hear about Nibiru's impending arrival, remember, the sky isn't hiding a killer planet. It's too busy revealing genuine wonders, ones far more fascinating than any myth. Hollywood loves a dramatic death in space, limbs flailing, eyes bulging, then pop, a gruesome explosion of gore as the vacuum tears a body apart. It makes for unforgettable cinema, but here's the cold, hard truth: space won't make you explode. The reality is far slower, more insidious, and in some ways even more terrifying. Without a spacesuit, the human body faces a brutal series of physiological failures, but your skin won't rupture like an overinflated balloon. Let's break down what actually happens. The vacuum of space creates an extreme pressure difference. Your body's internal pressure pushes outward while nothing counters it from outside. This causes immediate swelling as fluids vaporize, particularly in soft tissues like the eyes, tongue, and lungs. Within seconds, your saliva would boil at body temperature, not from heat, but because the lack of pressure lowers the boiling point. You'd lose consciousness in about 15 seconds as oxygen departs your bloodstream, but your circulatory system wouldn't fail instantly. Your skin, surprisingly resilient, would hold you together despite the swelling, thanks to its elasticity and the collagen fibers acting like a natural containment suit. The myth's origins are easy to trace. Films like Total Recall and Mission to Mars lean into visceral shock value, but the closest real-world example comes from a tragic NASA accident in 1965. During a test in a vacuum chamber, a technician's suit leaked, exposing him to near-space conditions for roughly 30 seconds. He reported the sensation of saliva boiling on his tongue before passing out, but he survived with no explosive trauma. Even in the vacuum of space, death wouldn't come from bursting. It would come from asphyxiation or fatal embolism, where gas bubbles form in the bloodstream, blocking circulation. Why does this distinction matter? Because space is deadly enough without embellishment. The real horror isn't in cartoonish explosions, it's in the silence. No sound carries your screams, no pressure lets you draw breath. Radiation fries your cells unchecked. Yet for all its lethality, space respects the tensile strength of human skin. That's the paradox of the cosmos. It's indifferent, not vindictive. It kills by absence, not violence. So next time you see an astronaut dramatically explode on screen, remember, the universe doesn't deal in special effects. Its dangers are quieter, stranger, and in their own way, more awe-inspiring than any fiction. And that's a truth worth holding onto, even if it doesn't make for a blockbuster moment. Back in 1976, NASA, a Viking 1 orbiter, snapped a photo of the Martian surface that sent shockwaves through the world, a formation in the Cydonia region that looked uncannily like a giant, sculpted face staring up at the cosmos. With symmetrical eyes, a pronounced nose, and even what appeared to be a mouth, it was too perfect to be natural. Headlines screamed about ancient alien civilizations, lost cities on Mars, and even extraterrestrial messages meant for humanity. Decades later, the truth is far less dramatic but no less fascinating. That iconic face on Mars isn't a monument, it's a mesa, a wind-scoured rock formation that just happened to catch the light in a way that fooled our pattern-seeking brain. Here's how the illusion unfolded. The original Viking image was low resolution, captured from an angle where sunlight cast deep shadows across the mesa's ridges. Combine that with the grainy quality of early space photography, and suddenly, a perfectly ordinary geological feature became a cosmic Rorschach test. Scientists call this phenomenon pareidolia, the human tendency to see familiar shapes, especially faces, in random patterns. It's why we spot bunnies in clouds, the man in the moon, or even religious figures on toast. Our brains are hardwired to prioritize facial recognition, a survival mechanism so ingrained that it sometimes misfires, turning cliffs into kings and rocks into ruins. But the real nail in the coffin for the face myth came from modern technology. When NASA Mars Global Surveyor revisited Cydonia in 1998 and again in 2001, its high-resolution cameras revealed the truth. No carved eyes, no enigmatic smile, just a weathered, lumpy hill about 3 kilometers long. The later Mars Reconnaissance Orbiter drove the point home with even sharper images. showing a landscape pockmarked by erosion, not artistry. The face was nothing more than an interplay of light, angle, and the human mind's hunger for meaning in the unknown. What makes this myth endure despite overwhelming evidence? It's the allure of cosmic companionship, the idea that we might not be alone, that someone or something out there left a calling card. The face became a canvas for our hopes and fears, a symbol of the mysteries Mars seemed to hold, but the reality is even more compelling. Mars does have wonders, canyons dwarfing the Grand Canyon, polar ice caps, and evidence of ancient water, but they're geological, not archaeological. The planet's true story, written in layers of rock and dust, is about the forces that shape worlds, not civilizations. So the next time you see a shadowy figure in a grainy photo or a face in the cliffs of another planet, remember, the universe isn't playing hide and seek. It's our own minds searching for reflections of ourselves in the cosmic void, and maybe that's the most human thing of all. You've probably heard the stories: emergency rooms overflowing during a full moon, police bracing for chaos, even nurses swearing births spike when the lunar glow is brightest. The idea that the moon tugs not just on tides but on human behavior is one of the most persistent myths in modern culture. It's woven into our language. Lunatic comes from the Latin luna, meaning moon, and reinforced by centuries of folklore. But when scientists actually crunched the numbers, they found something startling. The data doesn't just fail to support the myth, it actively contradicts it. Take crime rates, for example. Multiple studies, including analyses of police reports spanning decades, show no correlation between lunar phases and violent incidents. One comprehensive review in the journal Psychological Reports examined over 100 studies and found zero consistent evidence linking the full moon to aggression, accidents, or psychiatric emergencies. Even in professions where the belief is strongest, like nursing or law enforcement, objective records don't back up the anecdotes. Why? Because human memory is selective. We notice when something dramatic happens under a full moon but forget the dozens of quiet nights when nothing occurs. That's confirmation bias in action, our tendency to remember hits and ignore misses. Then there's the birth rate myth. Despite old wives' tales about full moons inducing labor, massive studies like one analyzing over 5 million births in North Carolina found no lunar influence. The moon's gravitational pull on Earth is real, but it's far too weak to affect something as small as a human body. Think about it. If the moon could sway childbirth, why wouldn't it also disrupt your coffee cup or houseplant? The math just doesn't add up. So why does this myth cling so stubbornly to our collective psyche? Part of it is cultural inertia. From werewolf legends to Shakespeare's moonstruck lovers, we've been taught to see the moon as a celestial puppet master. But there's also a deeper, more universal truth at play. We crave patterns. The night sky has always been humanity's first storybook, and connecting lunar cycles to life's chaos gives us a sense of control, even if it's illusory. The real lesson here isn't just about debunking myths. It's about how easily our perceptions can warp reality. The next time you hear someone blame the full moon for a sleepless night or a hectic shift, remember, the moon's magic is real, but it's the kind that inspires poets, not the kind that rewrites science. And maybe that's enough. After all, a universe where moonlight stirs our imagination is far more interesting than one where it dictates our actions. Space might seem like the ultimate deep freeze, a vast, dark void where temperatures plunge to hundreds of degrees below zero. But here's the cosmic twist: space isn't uniformly cold. In reality, it's a place of wild temperature extremes, where an object can bake in blistering heat on one side while its shadowed side freezes solid. This isn't just a quirky detail. It's a fundamental difference in how heat behaves when there's no air to spread it around. Picture an astronaut floating outside the International Space Station. The side of their suit facing the sun might reach a scorching 120 degrees Celsius, hot enough to boil water, while the opposite side, shielded from sunlight, could plummet to minus 150 degrees. That's a 270-degree swing across a single human body. On Earth, our atmosphere acts like a giant temperature regulator, distributing heat through convection and conduction. But in the vacuum of space, heat travels only through radiation, leaving objects at the mercy of direct exposure. This has real consequences for spacecraft design. Probes sent to the Moon or Mars have to endure days of relentless solar heating followed by weeks of frigid darkness. Engineers use reflective coatings, rotating components, and even heat pipes to manage these swings, because without careful planning, instruments can crack from thermal stress or overheat to failure. The Apollo missions faced this firsthand. Lunar modules had to withstand 300-degree temperature gaps between sunlight and shadow, a challenge as daunting as navigating the landing itself. So why does the "space is freezing" myth persist? It's partly because we conflate temperature with how we experience it. On Earth, cold often feels absolute. A winter day chills everything evenly. But space doesn't work that way. The cosmic backdrop may hover near absolute zero, but an object's temperature depends entirely on its relationship to energy sources like stars or nearby planets. A comet soaring toward the sun might develop a tail of vaporized ice not because space warmed up, but because sunlight struck its surface directly, bypassing any atmosphere that could soften the blow. The truth is, space isn't just cold or hot, it's both, often simultaneously. It's a reminder that the universe defies simple labels, operating by rules that can seem alien until we peel back the layers. And that's what makes exploration so thrilling. Every assumption we test reveals a cosmos far more dynamic than we imagined. For centuries, sailors and stargazers have looked to Polaris, the North Star, as a guiding light, literally. Its steadfast position above Earth's northern axis made it a celestial compass, the one constant in a spinning sky. But here's the cosmic irony. While Polaris is legendary for its navigational prowess, it's far from the brightest beacon in the heavens. In fact, it doesn't even crack the top 40. Sirius, the dog star, blazes 25 times more luminous, and Canopus, the southern sky's gem, outshines it by an even wider margin. So how did a relatively modest star become so iconic? The answer lies not in astronomy, but in human ingenuity. Polaris owes its fame to a fluke of planetary geometry. Earth's axis happens to point almost directly at it, making it appear stationary while other stars wheel around it nightly. This unique trait made it invaluable to ancient navigators, from Phoenician traders to Polynesian voyagers. But brightness had nothing to do with it. In reality, Polaris is a variable star, subtly pulsing in luminosity over days. Its light is steady enough to guide, but unremarkable compared to Sirius's dazzling white-blue glare or Vega's sapphire brilliance. The myth persists because we conflate utility with grandeur, a classic case of cultural significance overshadowing scientific fact. Consider how differently we'd view Polaris if Earth's axis tilted toward, say, Sirius. Suddenly, the night sky's brightest star would also be its navigational anchor, and the myth might never have taken root. But nature doesn't work that way. Polaris earned its reputation through sheer cosmic coincidence, not stellar firepower. Even its North Star status is temporary. Thanks to Earth's axial wobble called precession, the pole will drift toward Vega in about 12,000 years, a reminder that even our celestial landmarks are fleeting. The lesson here: humanity has a habit of assigning meaning where none inherently exists. We crowned Polaris king of the night sky, not because it was the most radiant, but because it was the most useful. And that's the real magic of astronomy. It teaches us to see the universe not just as it is, but as we've learned to navigate it, sometimes through brilliance, sometimes through sheer practicality. The stars don't care about our myths, but they'll always guide us home. The Van Allen radiation belts sound like something out of a sci-fi nightmare, twin rings of charged particles trapped by Earth's magnetic field, swirling around our planet with enough intensity to fry electronics and flesh alike. Conspiracy theorists love to claim these belts are an impenetrable barrier, proof that manned spaceflight beyond low Earth orbit is impossible without lethal radiation exposure. If that were true, though, how did Apollo astronauts sail right through them on their way to the moon not just once, but 6 times between 1968 and 1972? The answer isn't some government cover-up. It's a masterclass in precision engineering and orbital mechanics. First, let's demystify the belts themselves. Discovered in 1958 by physicist James Van Allen, these donut-shaped zones are filled with protons and electrons zipping around at near light speed. The inner belt stretches from about 600 to 6,000 kilometers above Earth, while the outer belt spans 13,000 to 60,000 kilometers. Dangerous, absolutely, but here's the critical nuance: they're not a solid wall of radiation. The belts have gaps, and their intensity varies based on solar activity and altitude. NASA early missions like Explorer 1 mapped these variations meticulously, allowing engineers to chart safe trajectories, like threading a needle through the least hazardous regions. Now consider the Apollo missions. Each spacecraft spent roughly 15 minutes traversing the belts at high speed, with the crew shielded by the aluminum hull of their command module. While the dose was higher than on Earth, about the equivalent of a chest X-ray, it was far below lethal levels. Modern spacecraft like Orion use even smarter shielding, layers of polyethylene and other materials that scatter or absorb radiation particles. Astronauts also time their launches to avoid solar storms, which can temporarily intensify the belts. It's not about bulldozing through a death zone. It's about navigating with respect, like a sailor steering around a reef. The real irony: the Van Allen belts aren't even the biggest radiation threat in space. Astronauts on the International Space Station, those shielded by Earth's magnetic field at that altitude, still absorb 10 times more cosmic rays per year than the average person on the ground. A trip to Mars, with its thin atmosphere and lack of a global magnetic field, poses a far greater challenge. But that's the point: space agencies openly discuss these risks while developing solutions, from water-lined walls to pharmaceutical countermeasures. The belts aren't a secret Achilles heel. They're a well-studied obstacle that science has learned to mitigate. So why does this myth persist? Because radiation is invisible and poorly understood, making it ripe for exaggeration. But the truth is far more inspiring. The Van Allen belts aren't a cosmic stop sign, they're a testament to human ingenuity. Every time an astronaut slips past them, they're not cheating physics. They're proving that with enough knowledge, even the universe's harshest environments become highways, not dead ends. Einstein's theory of relativity gave us one of the most mind-bending ideas in physics: the faster you move through space, the slower you experience time. It's a concept that's been twisted into a popular sci-fi trope. Hit light speed and time grinds to a halt. Cue dramatic scenes of frozen starscapes and astronauts watching civilizations rise and fall in the blink of an eye. But here's the reality check: time doesn't actually stop at light speed. It bends, stretches, and warps in ways that defy intuition. but the universe doesn't have a pause button, even for light itself. Let's unpack why this myth misses the mark. According to special relativity, time dilation isn't an on-off switch, it's a sliding scale. As an object accelerates closer to the speed of light, time for that object appears to slow down from the perspective of an outside observer. A clock on a speeding spaceship would tick slower than one on Earth, but crucially, it wouldn't ever stop ticking. The equations show that time dilation approaches infinity only as speed approaches light speed, but reaching that exact velocity is impossible for anything with mass. Even photons, the massless particles of light, don't experience time stopping from their frame of reference. Time doesn't exist at all. Their entire existence, from emission to absorption, is instantaneous, but that's a quirk of their massless nature, not a universal rule. Where did the confusion come from? Part of it stems from oversimplifying thought experiments like the twin paradox, where one twin traveling near light speed returns to find their sibling aged decades. Pop culture latched onto the extreme end of this idea, ignoring the nuance. But relativity isn't about freezing time, it's about relationships between frames of reference. An astronaut moving at 99.9% light speed would still perceive their own time passing normally. It's only when comparing their experience to someone else's that the staggering differences emerge. The deeper truth here is even more fascinating. Time dilation isn't some abstract theory, it's measurable. Atomic clocks on GPS satellites, orbiting at a mere 14,000 kilometers per hour, run ever so slightly faster than those on Earth's surface due to their speed and weaker gravity. If we didn't account for this, GPS accuracy would drift by kilometers within days. That's relativity in action, not as a hypothetical, but as a daily necessity. So why does this myth persist? Because the human brain struggles with scales beyond everyday experience. We're wired to think in terms of absolute time, where a second is a second for everyone, everywhere. Relativity shatters that intuition, revealing a universe where time is as flexible as taffy. But flexibility isn't the same as stoppage. The cosmos doesn't do absolute, it trades in relationships, perspectives, and limits we're still learning to navigate. And that's the real wonder, not a universe where time freezes, but one where it dances. We often picture the universe as a vast, hollow expanse, a cosmic cathedral where stars and planets drift through endless nothingness. But this image couldn't be further from the truth. What we perceive as empty space is actually a seething, invisible ocean of energy and matter, so dense with hidden activity that calling it empty is like calling the internet quiet because we can't hear the data. The reality, less than 5% of the universe is made up of the stuff we can see, stars, galaxies, and nebulae. The rest is a cryptic cocktail of dark matter and dark energy, forces so dominant they dictate the fate of the cosmos, yet remain utterly invisible to our eyes. Let's start with quantum fields, the universe's invisible scaffolding. Even in the deepest voids between galaxies, space is never truly empty. It's humming with quantum fluctuations, particles flickering in and out of existence so fast we can't detect them directly. These aren't just mathematical abstractions. They've been measured in labs through effects like the Casimir force, where two metal plates in a vacuum inexplicably pull together because of the particle activity between them. Imagine dipping your hand into what looks like still water, only to feel it crackling with unseen currents. That's the quantum vacuum, a froth of potential, where nothing is anything but. Then there's dark matter, the universe's silent architect. We can't see it, touch it, or even interact with it electromagnetically, yet its gravitational pull is the only thing keeping galaxies from flying apart. Picture a spiderweb so fine it's invisible, yet strong enough to catch a falling boulder. That's dark matter, an unseen framework woven through every galaxy, bending light and sculpting the cosmos on scales we're only beginning to map. Without it, stars on the edges of galaxies would orbit slower than they do, like cars on a highway, mysteriously speeding up despite no pressure on the gas. And then there's the real enigma, dark energy. This mysterious force isn't just hiding in the corners of space. It is space woven into its very fabric. Think of it as anti-gravity, pushing the universe apart faster and faster, counteracting everything we thought we knew about cosmic expansion. It makes up nearly 70% of the universe's energy budget, yet we have no idea what it actually is. The closest analogy: imagine blowing up a balloon with invisible ink. You can't see what's stretching it, but you watch the dots on its surface race away from each other, helpless against the unseen force. So why does the empty universe myth persist? Because we're visual creatures. If we can't see it, it might as well not exist. But the cosmos doesn't care about our sensory limits. Every cubic light year of so-called emptiness is a theater of invisible forces, a reminder that what we perceive is just the tip of the cosmic iceberg. The universe isn't mostly empty, it's mostly unknown, and that's the most thrilling truth of all. For generations, we've been taught that gold, that shimmering symbol of wealth and beauty, owes its existence to the violent deaths of massive stars, supernovas. It's a dramatic origin story, a star collapsing in on itself, unleashing unimaginable energy and forging heavy elements in its final moments. But here's the cosmic plot twist: supernovas aren't the only celestial alchemists at work. Some of the gold in your jewelry, the rings on your fingers, or even the circuitry in your phone might have been born from something far rarer and more spectacular: the collision of neutron stars. Imagine two city-sized remnants of dead stars, each so dense that a teaspoon of their material would weigh 1 billion tons, locked in a gravitational dance. As they spiral closer, their immense gravity distorts spacetime itself until finally they collide. The impact is so cataclysmic that it ripples through the fabric of the universe as gravitational waves, detectable across billions of light years. But that's not all. In the aftermath, a forge unlike any other ignites. The extreme conditions, temperatures reaching trillions of degrees and pressures beyond comprehension, create a nuclear cauldron where atoms are smashed together, forming heavy elements like gold, platinum, and uranium. These precious metals are then flung into space in glowing, radioactive clouds, eventually seeding future generations of stars and planets. This isn't just theoretical. In 2017, astronomers witnessed this very process in action. When gravitational wave detectors picked up the signal of two neutron stars merging, telescopes around the world swung into action, capturing the aftermath. The event, dubbed GW170817, wasn't just a fireworks show, it was a gold factory. Spectroscopic analysis of the light revealed signatures of heavy elements, including gold, being synthesized in real time. Researchers estimated that the collision produced an amount of gold equivalent to several times the mass of Earth. Suddenly, the idea that supernovas were the sole source of our planet's precious metals seemed quaint. So why has the supernova myth persisted for so long? Part of it comes from the undeniable drama of these stellar explosions. They are easier to visualize and far more common than neutron star mergers. But the deeper truth is that cosmic chemistry is messy. Supernovas do create heavy elements, just not as efficiently as we once thought. Neutron star collisions, though rare, are like precision workshops specializing in the heaviest of metals. It's a division of labor on a galactic scale, with different cosmic events contributing to the periodic table in their own way. This revelation changes how we see our place in the universe. Every time you hold a piece of gold, you're touching stardust, but not just any stardust. You're holding remnants of one of the most violent and beautiful events in existence, a fleeting moment when dead stars collide and scatter their treasures across the cosmos. The next time you gaze at the night sky, remember, the universe doesn't just create gold in death, it forges it in resurrection. The Hubble Space Telescope has gifted us some of the most breathtaking images in astronomy: spiral galaxies swirling like cosmic fingerprints, nebulae glowing with newborn stars, and galaxies so distant their light has traveled billions of years to reach us. It's no wonder people assume Hubble's piercing gaze can peer all the way back to the Big Bang itself. But here's the cosmic catch. While Hubble is a time machine of sorts, it can't see the universe's fiery birth. That revelation belongs to an entirely different kind of instrument, one designed to detect whispers from the cosmos' earliest moments. The confusion stems from a mix-up between two distinct cosmic records. Hubble's deepest images, like the iconic ultra-deep field, capture galaxies as they existed just 400 million years after the Big Bang, an astonishing feat, but still a cosmic heartbeat away from the beginning. The actual afterglow of the Big Bang, called the cosmic microwave background, or CMB, is something else entirely. This faint microwave radiation fills the entire universe, a relic from when the cosmos was a seething plasma just 380,000 years old. It's not starlight or galaxies, it's the cooled remnants of the universe's first light, stretched over 13.8 billion years into a ghostly microwave hum. So why can't Hubble see it? The answer lies in wavelengths. Hubble's instruments are tuned to visible, ultraviolet, and near-infrared light, perfect for spotting galaxies, but blind to the CMB's microwave signature. Detecting that primordial glow requires specialized tools like the Planck satellite or the COBE probe, which map the CMB's subtle temperature variations with exquisite precision. These instruments don't rely on mirrors and lenses like Hubble. They use radio antennas and cryogenic detectors to pick up the universe's faintest thermal whispers. The difference is like comparing a high-resolution camera to a heat-sensitive night vision scope. Both reveal hidden layers of reality, but in utterly different ways. This myth reveals a deeper truth about how astronomy works. No single telescope can do it all. Hubble shows us the universe's grand structures, while instruments like the James Webb Space Telescope peer through dust clouds to study star formation. Gravitational wave detectors like LIGO listen to spacetime's ripples, and neutrino observatories track particles from the sun's core. Each tool unlocks a different slice of cosmic history, like detectives piecing together a crime scene from fingerprints, DNA, and security footage. The CMB isn't Hubble's domain, it's a puzzle for radio astronomers and cosmologists, who have used it to uncover everything from the universe's age to the seeds of galaxy formation. The next time you marvel at Hubble's images, remember, they're just one chapter in a much bigger story. The universe doesn't reveal its secrets to a single observer. It demands an arsenal of instruments, each tailored to decode a different piece of the cosmic puzzle. And that's the real beauty of astronomy. It's not about one telescope's glory, but the collective effort to listen, watch, and unravel the universe's greatest mysteries, one wavelength at a time. We've all grown up learning about the 88 constellations officially recognized by the International Astronomical Union, the familiar shapes of Orion the Hunter, Ursa Major, and the Southern Cross. These star patterns form the backbone of modern astronomy, guiding telescopes and star charts alike. But here's the cosmic truth. The IU's constellations are just one chapter in humanity's celestial storybook. Across the globe and throughout history, cultures have mapped the night sky with entirely different stories, boundaries, and star groupings. To claim there are only 88 constellations isn't just inaccurate, it's a disservice to the rich tapestry of human imagination and observation. Consider the indigenous Australians who have read the Milky Way not as a hazy band of light, but as a river teeming with celestial creatures. To the Yolngu people, the dark patches within it form the great emu in the sky, its body stretching across the galaxy, its shape shifting with the seasons to signal when to gather eggs. Meanwhile, Polynesian navigators relied on star compasses that divided the sky into invisible houses, each governed by guiding stars like Hoculaire Arcturus and Hicyonalia Spica. These weren't just pretty pictures, they were precision tools for crossing thousands of kilometers of open ocean, long before European explorers dared to leave sight of land. Then there's ancient China, where astronomers organized the sky into 28 lunar mansions, each marking the moon's nightly resting place. The azure dragon of the east coiled across 7 constellations, while the black tortoise of the north guarded the winter solstice. Even the Inca saw the Milky Way as a celestial river, its dark dust clouds forming animal spirits that influenced agriculture and mythology. These systems weren't arbitrary, they reflected deep connections between celestial events and earthly cycles, woven into calendars, rituals, and survival strategies. So why did the IAU settle on 88? The answer lies in 20th century standardization, when Western astronomers formalized a system rooted largely in Greco-Roman mythology, with a few additions from the age of exploration. It's a practical framework, but one that inadvertently erased countless other celestial traditions. The irony, many of the IAU's constellations are already artistic liberties. Connect the dot exercises where ancient Greeks saw heroes and beasts, indigenous cultures might see canoes or ancestors. The stars themselves are neutral, it's we who project meaning onto them. This isn't just about nostalgia for forgotten star lore. It's about recognizing that science and culture have always been intertwined. When we dismiss non-Western constellations as mere folklore, we ignore how they advanced astronomy in their own right. The Maori used Matariki, the Pleiades, to mark the new year, while the Navajo saw the same cluster as the seeds of celestial corn. Both systems encoded sophisticated knowledge of seasonal changes, proof that science thrives in many forms. The next time you look up at the night sky, remember, those 88 constellations are just one way to navigate the cosmos. Beyond them lies a universe of stories, each a testament to humanity's endless curiosity. The stars haven't changed, only the eyes and the cultures interpreting them. And that's the real wonder of astronomy, not just mapping the heavens, but discovering how many ways there are to see them. Watch any video of astronauts aboard the International Space Station, and you'll see them gliding effortlessly, tools drifting from their hands, water droplets hanging suspended like tiny planets. It's easy to assume, as many do, that they're floating because they've escaped Earth's gravity, that somewhere between launch and orbit, the familiar tug of our planet's pull simply vanishes. But here's the reality that defies intuition. Gravity up there is almost as strong as it is down here. If you could stand on a scale at the ISS's altitude, about 400 kilometers up, it would show you weigh barely 10% less than on the ground. So why don't astronauts plummet back to Earth? Because they're not beyond gravity's reach, they're mastering it in a celestial dance of perpetual free fall. Think of it like this. Imagine throwing a baseball so hard that, as it arcs toward the ground, Earth's curvature drops away beneath it at the same rate. The ball would keep falling but never hit the ground, tracing an endless loop around the planet. That's precisely what the ISS does, hurtling forward at 28,000 kilometers per hour, fast enough to ensure that with every meter it falls toward Earth, the planet's surface curves away by the same amount. The result isn't zero gravity, It's microgravity, a delicate equilibrium where everything inside the station falls together at the same rate, creating the illusion of weightlessness. This myth's persistence stems from a mix of terminology and Hollywood physics. Films often depict space as a gravity-free zone where characters float the moment they leave Earth's atmosphere. But gravity doesn't just switch off. Even the moon, nearly 400,000 kilometers away, feels Earth's pull. That's what keeps it in orbit. The real magic lies in how orbit works, not as an escape from gravity, but as a perfect balance between speed and pull. Too slow and you'd spiral downward, too fast and you'd break free entirely. The ISS threads this needle flawlessly, making one full lap around Earth every 90 minutes, its crew in a constant state of controlled falling. Here's where it gets even more fascinating. Astronauts don't just experience this weightlessness, they harness it. Without the constant downward force we take for granted, fluids in their bodies redistribute, spines elongate, and muscles atrophy unless rigorously exercised. These effects aren't signs of gravity's absence, but proof of its subtle dominance. Even the station itself feels gravity's whisper. Without occasional boosts from docked spacecraft, atmospheric drag would slowly pull it back to Earth. So why does this distinction matter? Because it reshapes how we see space travel. Floating isn't about leaving gravity behind. It's about moving with it in perfect synchrony. The next time you watch an astronaut somersault through the ISS, remember, they're not defying physics, they're riding it, a testament to human ingenuity turning the cosmos's most fundamental force into a playground. And that's far more extraordinary than any Hollywood zero-gravity fantasy. We picture galaxies as flawless pinwheels, symmetrical arms spiraling from a glowing core, like cosmic daisies frozen in space. But the Milky Way, our home galaxy, is anything but perfect. Recent observations reveal a warped, twisted disk that bends like a vinyl record left too long in the sun, its outer edges flaring upward at one end and drooping at the other. This isn't some artistic flourish, it's the signature of a violent past, written in the language of gravity and motion. The myth of the perfect spiral stems from an understandable limitation. For centuries, we mapped the Milky Way from inside it, like ants sketching the contours of a forest while standing beneath its canopy. Early astronomers, peering through telescopes at distant galaxies like Andromeda, assumed ours must mirror their elegant symmetry. But in 2019, the European Space Agency's Gaia mission delivered a cosmic reality check. By plotting the positions and motions of over 1 billion stars, it revealed our galaxy's disk isn't flat. It's an S-shaped curve, warped by gravitational turmoil. Some regions loom hundreds of light years above the galactic plane, while others plunge just as far below. So what's bending the Milky Way? The prime suspects are ancient collisions and dark matter's invisible hand. Around 3 billion years ago, a dwarf galaxy called Sagittarius, itself now torn apart, slammed into ours like a pebble tossed through a spiderweb. The impact sent ripples through the disk, distorting its shape. Meanwhile, dark matter, that mysterious substance outweighing visible stars 5-to-1, tugs unevenly on the galaxy's outskirts. Think of it as a cosmic game of tug-of-war, where unseen players twist the rope into knots. The real irony, those textbook images of pristine spirals are partly to blame. Artists often smooth out the chaos to create visually pleasing diagrams, inadvertently reinforcing the myth. But nature doesn't do perfection. Even the Milky Way's famed arms, long depicted as neat, continuous arcs, are more like frayed ribbons, studded with star-forming regions and gas clouds that break the illusion of order. This revelation changes how we see our place in the cosmos. The Milky Way isn't some static monument. It's a dynamic, messy beast, still bearing the scars of its violent youth. Its warped disk is a testament to the universe's restlessness, a reminder that even galaxies can't escape the forces that shape them. And perhaps that's the real beauty of astronomy, not the pursuit of perfect models, but the thrill of uncovering the glorious imperfections hidden in plain sight. Here's a cosmic paradox that might make you double-check everything you learned in grade school. When Earth is actually farthest from the Sun in early July, the northern hemisphere is baking in summer heat. Meanwhile, in January, when we're closest to the Sun, half the planet is shivering through winter. If distance doesn't dictate seasons, what does? The answer lies in a simple but profound celestial quirk. Earth's axis is tilted like a spinning top frozen mid-lean, and that 23.5-degree slant is the real maestro behind the symphony of spring blossoms, summer scorches, autumn leaves, and winter frost. Picture Earth as a globe slightly knocked off kilter, with an invisible rod, the axis, piercing through the north and south poles. As our planet orbits the Sun over the course of a year, this tilt means one hemisphere consistently leans toward the Sun for part of the orbit, while the other leans away. When the North Pole angles sunward, sunlight strikes the northern hemisphere more directly, concentrating its energy over smaller areas and delivering longer days. That summer, 6 months later, as Earth continues its journey, the North Pole tilts away, spreading sunlight thinly across the hemisphere and shortening daylight hours, winter's signature. Meanwhile, the Southern Hemisphere experiences the opposite cycle, which is why Australians celebrate Christmas in beach weather. But here's where the myth gets sticky. Earth's orbit is elliptical, meaning our distance from the Sun does vary by about 5 million kilometers between January's closest approach, perihelion, and July's farthest point, aphelion. So why doesn't this drastic distance shift override the seasons' simple math? While 5 million kilometers sounds vast, it's only a 3% difference in solar exposure. Nowhere near enough to overpower the tilt's effects. In fact, the Southern Hemisphere, which leans toward the Sun during perihelion, gets slightly more intense summers than the Northern Hemisphere, but the tilt's influence still dominates. The persistence of this myth reveals how easily intuition can mislead us. After all, standing by a campfire teaches us that stepping closer means more heat, so why wouldn't the same logic apply to planets and stars? But space operates on different rules. Sunlight isn't just about proximity, it's about angle. A flashlight beam shining straight down onto a table lights a small, bright circle, but tilted, and the light stretches into a faint oval. Earth's tilt does the same with sunlight, diluting or concentrating its warmth across continents. Historical stargazers like the ancient Greeks actually got closer to the truth than many modern myth believers. They noticed that the Sun's path across the sky shifted higher in summer and lower in winter, though they didn't grasp the axial tilt's role. Today, we have satellites like NAS, a solar dynamics observatory, tracking these shifts in real time. Yet the distance myth lingers, perhaps because it offers a simpler, if wrong, explanation. The real wonder here isn't just the mechanics of seasons, it's how Earth's tilt weaves them into the fabric of life. Without that slant, our planet would have no seasons at all, just eternal temperate belts frozen in climate stasis. No monsoon rhythms, no migratory cues for animals, no harvest cycles. That tilt is the reason maple trees blaze red in October and why tulips know when to push through thawing soil. It's a reminder that sometimes the most profound forces aren't the obvious ones. The universe doesn't always follow our earthly logic, and that's what makes uncovering its truth so thrilling. You might hear someone say that galaxy is 1,000 light years away, and assume they're talking about time like it'll take 1,000 years to get there. But here's the cosmic twist. A light year isn't a measure of time at all. It's a distance, a yardstick for the unimaginably vast stretches between stars. Think of it like this: if you could ride a beam of light, it would take you 1 year to travel a single light year. That's about 9.5 trillion kilometers, a number so large it's almost meaningless to our everyday experience. Yet in astronomy, where stars are separated by voids so enormous that kilometers become useless, light years are the perfect unit. The confusion makes sense. The name itself, light year, sounds like it's tied to time, and we're used to measuring travel in hours or years, but the key difference lies in what's being measured. Just as a kilometer per hour tells you speed, not distance, a light year tells you how far light travels in a vacuum over a year, not how long the trip takes. This distinction matters because space doesn't obey our terrestrial rules. Proxima Centauri, the closest star to our Sun, is 4.2 light years away. That doesn't mean we're seeing it as it was 4.2 years ago, though that's also true. It means the space between us and that star is so vast that light itself, the fastest thing in the universe, needs over 4 years to cross it. This myth's persistence reveals a deeper quirk of human psychology. We're wired to think in terms of time because that's how we experience movement, driving to another city. You'd say it's 3 hours away, not 300 kilometers, but space flips that logic. The Andromeda Galaxy isn't 2.5 million years away. It's 2.5 million light years, a distance so colossal that even if you could travel at light speed, you'd still need generations to reach it. That's why astronomers prefer light years. They collapse these impossible distances into manageable numbers, giving us a way to grasp the universe's scale without drowning in zeros. Here's where it gets even more mind-bending. Because light takes time to reach us, looking across light years does mean looking back in time. When you gaze at Sirius, the brightest star in our night sky, you're seeing it as it was 8.6 years ago. But the light year itself isn't the time machine, it's the ruler that measures how far that ancient light traveled. The universe is constantly showing us its past. Light years just help us understand how far into the past we're peering. So next time you hear light year, remember, it's not a countdown or an eater. It's the universe's way of reminding us that space is so vast, even light has to hustle. And that's a humbling thought. No matter how fast we go, the cosmos will always keep its distance. Few natural wonders spark as much awe and wild speculation as the auroras. Those shimmering curtains of green, pink, and violet dancing across polar skies have been mistaken for everything from dragon fire to spirits of the dead. But one modern myth stands out: the idea that these lights are alien signals, some interstellar Morse code meant for humanity. The truth is far more fascinating and rooted in the delicate interplay between our planet and the sun. When solar storms erupt, they hurl charged particles across space at millions of kilometers per hour. Earth's magnetic field catches these particles like a cosmic fishing net, funneling them toward the poles. There, they collide with oxygen and nitrogen atoms in the upper atmosphere, transferring energy that gets released as light. Oxygen glows green or red, while nitrogen produces blues and purples, a celestial light show powered entirely by physics, not extraterrestrial engineers. Indigenous Arctic cultures understood this phenomenon long before modern science. The Sami people called the Auroras Gu of Sahas, meaning the light you can hear, believing them to be the energies of the departed. Inuit legends described them as spirits playing ball with a walrus skull, while Scandinavian folklore saw them as reflections from the shields of Valkyries. These interpretations weren't just poetry, they were careful observations of patterns, noting how the lights flared during cold, clear nights and quieted when the wind shifted. So where did the alien myth take hold? blame our love for sci-fi tropes. From close encounters of the third kind to viral conspiracy theories, pop culture has repurposed the auroras as everything from alien highways to interdimensional portals. The irony, real auroras do carry messages, just not the kind UFO enthusiasts imagine. Scientists study their colors and shapes to predict solar storms that could knock out satellites or power grids, turning folklore into a tool for planetary defense. The next time you see those rippling lights, remember, you're witnessing one of the solar system's most beautiful conversations. Earth's magnetic field whispering to the solar wind, ancient cultures decoding its rhythms, and modern science unraveling its secrets, all without a single alien antenna in sight. Some truths don't need extraterrestrial explanations to feel magical. The universe writes its own poetry, and the auroras are its brightest verses. We often imagine the universe as an endless, boundless expanse, an infinite ocean of galaxies stretching forever in every direction. This idea feels intuitive, almost comforting in its grandeur, but here's the cosmic reality check. While the universe is unimaginably vast, we have no evidence it's truly infinite. In fact, everything we can observe, every star, every galaxy, every flicker of light fits within a finite bubble called the observable universe, a region about 93 billion light-years across. Beyond that, the answer isn't just unknown, it might be fundamentally unknowable. This myth stems from a subtle but crucial mix-up between two concepts, the entire universe and the observable universe. The observable universe is the portion of space from which light has had time to reach us since the Big Bang, 13.8 billion years ago. Because the universe is expanding, the farthest edges of this bubble aren't 13.8 billion light-years away. They're much farther, stretched by the relentless growth of space itself. But here's the catch. We can't see beyond this horizon, not because our telescopes aren't powerful enough, but because light from more distant regions hasn't had time to reach us yet. It's like standing in a foggy forest. You can only see so far before the mist swallows everything. Now, does that mean the universe stops at the edge of what we can observe? Not necessarily. Cosmologists debate whether the cosmos is infinite or merely extremely large. But here's the twist: we may never know for sure. If space stretches infinitely beyond our observational horizon, those regions are forever cut off from us, receding faster than light can bridge the gap. Even in principle, no signal, no probe, no future technology could ever reach them. The universe could be infinite, but from our vantage point, it might as well not be. This isn't just philosophical musing. It has real implications for how we understand the cosmos. An infinite universe would mean countless copies of Earth, infinite versions of you reading infinite variations of this sentence, a mind-bending idea called the inflationary multiverse. But a finite universe would imply boundaries, edges, or perhaps even a looping geometry where traveling far enough in one direction brings you back where you started. The problem: both ideas are untestable with current science. The universe, in its cruel humor, keeps its ultimate size just out of reach. So why does the infinite universe myth persist? Because infinity is seductive. It's easier to picture an endless cosmos than to grapple with the paradox of a universe that's finite but unbounded, or one that's infinite in theory but finite in practice. But the real wonder lies in what we can confirm. The observable universe, for all its limits, contains 2 trillion galaxies, each with billions of stars, and more planets than grains of sand on all Earth's beaches. That's enough grandeur to last a lifetime of exploration without needing infinity to impress. The next time you gaze at the night sky, remember, the universe doesn't owe us answers to every question. Some mysteries might remain forever veiled, not because science has failed, but because the cosmos itself has drawn the curtains, and in a way that's more thrilling than any myth. A universe that keeps secrets is a universe that never stops surprising us. Space travel does bend time, just not in the way Hollywood blockbusters would have you believe. The idea that astronauts return from missions significantly younger than those of us stuck on Earth makes for great sci-fi drama, but the reality is far more subtle. Thanks to Einstein's theory of relativity, time does pass slower for objects moving at high speeds or experiencing strong gravity. This effect, called time dilation, is real, but unless you're planning an interstellar road trip at near light speeds, don't expect to cheat aging anytime soon. Take the International Space Station, where astronauts orbit at about 28,000 kilometers per hour. At that velocity, time dilation kicks in, but the difference is almost laughably small. After spending 6 months in space, an astronaut would age roughly 0.007 seconds less than someone on Earth. That's not even enough time to blink. Even Scott Kelly, who logged 540 consecutive days in orbit, a record for NASA, had gained only about 20 milliseconds of youth relative to his twin brother Mark. Hardly the fountain of youth some imagine. The confusion stems from relativity's more extreme thought experiments. If you could board a starship traveling at 90% the speed of light, time dilation would become dramatic. A 5-year journey at that speed would mean returning to an Earth that had aged over 11 years. Push closer to light speed, and the effect grows exponentially. But here's the catch. Reaching those velocities requires energy levels far beyond our current technology, or even theoretical plausibility. The cosmic speed limit isn't just a suggestion. It's a fundamental barrier woven into the fabric of spacetime. Gravity's role in time dilation is equally oversimplified. Near a black hole's event horizon, where gravity warps spacetime severely, clocks would crawl compared to distant observers. Yet in Earth's orbit, the weaker gravity only tweaks time dilation by microseconds. The movie Interstellar got one thing right. Near a supermassive black hole, hours could equal years elsewhere. But unless you're planning a vacation to Gargantua, your biological clock will keep ticking in lockstep with everyone else's. So why does this myth persist? Relativity is notoriously mind-bending, and pop culture latches onto its most sensational implications. But the truth is just as fascinating. Those minuscule time shifts might seem trivial, but they're proof that Einstein was right. Time is flexible, even if we can't yet harness it. GPS satellites account for time dilation daily, adjusting their clocks to stay synchronized with Earth's surface. Without these corrections, navigation apps would misplace you by kilometers within hours. The real takeaway: space travel does change time, just not in ways that rewrite human lifespans. For now, aging slower in space remains the stuff of fiction. But the fact that we can measure these tiny effects at all is a testament to how precisely we've learned to read the universe's hidden rhythms. And who knows? Maybe one day, if we crack the secrets of near-light speed travel, our descendants will laugh at how quaint our early misconceptions were. Until then, the only way to stay young is the old-fashioned way: take care of your body and keep looking up at the stars. We all know the moon's gravity tugs at Earth's oceans, lifting entire seas into rhythmic tides that shape coastlines and ecosystems. But to think that's all it does. That's like saying a symphony is just about the violin section. The moon's influence stretches far beyond shorelines. Its gravitational whispers ripple through rock, air, and even the slow dance of continents. Our satellite doesn't just move water, it bends the planet itself. Take Earth's crust, for example. While it's too rigid to slosh like the ocean, it isn't immune to the moon's pull. Precise GPS measurements reveal that the ground beneath your feet actually rises and falls by several centimeters with the lunar cycle. Cities like Tokyo, built on unstable sediments, can experience even greater shifts, enough to subtly stress fault lines. Scientists call these solid Earth tides, and while they're tiny compared to ocean tides, they're not trivial. In places like California's San Andreas Fault, researchers have detected correlations between these tidal stresses and the timing of small earthquakes. The moon doesn't cause quakes, but it might gently nudge them like a finger tapping a snow-laden branch. Then there's the atmosphere. The moon's gravity creates atmospheric tides, invisible waves of pressure that travel through the air, altering wind patterns and even rainfall distribution. Over the tropics, these lunar tides can strengthen afternoon thunderstorms by a measurable percentage. Sailors in the 18th century swore the moon affected the weather, and modern meteorology confirms they weren't entirely wrong. The effect is subtle, yes, drowned out by Earth's turbulent weather systems, but it's there, etched into the data. But perhaps the most surprising impact lies deep underground. The same forces that flex the crust also heat it. As rock stretches and compresses under lunar gravity, friction generates tiny amounts of warmth, enough that some scientists speculated could influence volcanic activity over geologic timescales. Iceland's volcanoes, for instance, erupt slightly more often during certain phases of the tidal cycle. Again, the moon isn't flipping switches on eruptions, but it's turning the dials just enough to leave a statistical fingerprint. So why does the tides-only myth persist? Because water's movement is obvious. You can watch the ocean retreat from a beach or surge into a bay, but the moon's other effects require instruments to detect: seismometers, satellite altimeters, barometers. Out of sight, out of mind. Yet every time you feel a breeze or hear the rumble of distant thunder, remember, the moon's gravity is there too, shaping our world in ways we're only beginning to measure. The tides are just the opening act in a much grander cosmic ballet, one where Earth isn't just a passive partner, but a responsive one, flexing, breathing, and echoing the rhythm of the sky. From lunar illusions to cosmic dimensions, we've dismantled 31 myths about our universe, replacing folklore with facts. Each revelation peels back another layer of cosmic mystery, showing us that reality doesn't just defy expectations, it rewrites them. Think about it, black holes aren't the vacuum cleaners of doom. The moon's far side isn't eternally dark, and space itself hums with hidden energy. These truths aren't just corrections, they're invitations to look deeper, to question the stories we've been told, and embrace the universe as it truly is: wild, untamed, and infinitely surprising. What makes this journey so thrilling isn't just the myths we've debunked, but the questions they leave in their wake. If gold comes from colliding neutron stars, what other cosmic alchemy is happening out there? If the Milky Way is warped, what else have we gotten wrong about galaxies? Every answered question sparks new ones, and that's the real magic of astronomy. It's not about memorizing facts, it's about learning how to wonder. So here's your challenge: take these truths and run with them. The next time you hear a cosmic claim, whether it's about rogue planets, alien megastructures, or time standing still, ask for the evidence. Dig into the science, because the universe doesn't reveal its secrets to passive observers. It rewards the curious, the skeptical, and the relentless. Now it's your turn. Drop a comment below. Was there a myth that shocked you? A truth that changed how you see the night sky? Or maybe there's a cosmic question still keeping you up at night? Let's keep the conversation going. And remember, the greatest discoveries often start with a simple act of looking up and daring to ask, what if the cosmos